Hello everyone, welcome back to our channel. Today we are going to discuss about a most popular optimization algorithm in machine learning. So that is stochastic gradient descent. So today we are going to cover the maths behind it and explain it with a simple example. So let's begin. First, we will define the problem we are going to solve. Suppose we have a data set with input x. So input is x and we have the output as y. We want to train a model that can predict the output y given a new input x. So we can do this by minimizing a cost function j that measures the difference between the predicted output and the true output. So j is equal to 1 by m into sum over I is equal to 1 to m y hat minus y whole square. So here m is equal to training example y hat is equal to the predicted output and y is equal to actual output. So this is the cost function calculation. So we want to find the parameters of our model that minimize the cost function. Stochastic gradient descent is an algorithm that can help us to do it. The basic idea behind the stochastic gradient descent is to update the parameters of our model in small steps based on the gradient of the cost function with respect to those parameters. We do this for each training example in our data set rather than all at once, which is what makes it stochastic. This is the update rule for stochastic gradient descent. Eta represent the parameter of our model. And alpha is equal to the learning rate. And derivative of cost function with respect to the theta is the gradient of the cost function with respect to theta. We compute this gradient for each training example and update the parameters accordingly. Let's look at a practical example to see how this works. Let's analyze an example of the stochastic gradient descent applied to a simple linear regression problem with one input feature. So that the data set is x is equal to just some random numbers and y is equal to and the random numbers. Our goal is to find the best prediction for this data using the mean squared error as our loss function. So mean squared error, so that means j is equal to 1 by n summation over I is equal to 1 to n calculated output minus actual output whole square. Sometimes this is taken as 2n just for the mathematical simplicity, because when the derivative will be taken, these two will come here and that will be nullified by these two. Now y hat is equal to, we know, like it is parameter of x. So if w is the weight and x is the input and b is the bias, so it will be w into xi plus b. The mean squared error will be summation over I is equal to 1 to n and 1 by total batch size into 2, and now y hat will be replaced by this, so it will be w into xi plus b minus y, so this whole square. So this is the loss function with respect to this data set. Now to use the stochastic gradient descent to minimize this mean squared error loss function, we would update our weight and bias iteratively based on a random sample subset of the data, and this is known as the mini batch. So now the update rule. So now we know based on this equation, like theta is equal to theta minus alpha, alpha is the learning rate, into derivative of the loss function with respect to theta. Now in our case, what is the theta? Theta is either b or w. So now if we calculate theta as w, then this will be w again minus alpha and then derivative of this j. So that will be calculated as alpha. Now we have 1 by m. So this is the mini batch size into I is equal to 1 to m and w xi plus b minus yi. So this into xi, right? And that 2 will be nullified. So now if we calculate for the b, b is equal to b minus alpha into, now that will be simple, there will be no xi here, right? Because b is not attached to any x value, x is equal to always 1 for bias case. So b minus alpha into 1 by m summation over I is equal to 1 to m, m is the mini batch size, w into xi plus b minus yi. So this is the bias value, how it is calculated. Now let's run it with the data. W is equal to 0, b is equal to 0, alpha is the hyperparameter, that is learning rate, so that controls the step size. So alpha is equal to, let's say, 0.01, and the mini batch size is equal to 1. So this batch size again is the number of data points in a single batch. So that is m is equal to 1. Now I will randomly taken the value from this. So let's say I will take this value, first value. Okay, so x is equal to 1 and y is equal to 2. We will use this value to update our weights and bias according to the stochastic gradient descent update rule. So we know the update rule. So if I just put this update rule, w is equal to w minus alpha into 1 by m, and then w into x plus b minus y. Now putting the value, w is equal to initial value 0, alpha is equal to 0.01, m is equal to 1, w is equal to again 0, x is equal to 1, b is equal to 0, and then y is equal to 2. So then that will be minus 0.01 into minus 2. So that will be 0.02. So that is the new value of the w after first iteration. Same way, if we calculate b, taking this, bias is equal to bias minus alpha into 1 by m. Now batch size is equal to 1. So that will be w into x plus b minus y, right? So putting the value, b is equal to 0, alpha is equal to 0.01, m is equal to 1, and then w is equal to 0, x is equal to 1, b is equal to 0, and y is equal to 2. So again it will be 0.01 into minus 2. So that will be 0.02. So w is equal to 0.02 after first iteration and b is equal to 0.02 after first iteration. We will take these values and go to the next iteration. So now if we do it programmatically, let's say for iteration is equal to 100 or 1000. If we do it programmatically using a Python code, so then we can easily say or see how this value is converging. This w and b value is converging to a certain value where the loss, the mean squared error loss, this is my loss function, is minimized. So let's see, we keep the same value for x and y. So x is equal to and y is equal to right? This is the value we have given when we did the whiteboard calculation. Now let's add the bias. X is equal to, so for bias case we know x is equal to 1 for all the bias. So now x will be and that will be concatenated with the actual x value. So just I am adding 1 for each of the x. So that is like another parameter with all value as x, and this is for the axis one. Now let's see what is the value of x. So it's just like the first thing is the bias value and second is the x value. Okay, and now let's initialize the weight and bias. So that will be theta 0 and theta 1. So theta 0 will be the bias and theta 1 will be the weight w. So let's put it as theta array. So this will be all zeros. Now we need to set the hyperparameters like learning rate. So learning rate will be same as whiteboard 0.01 and number of iteration. Let's put it 100. Now let's define a function to calculate the cost. So I'll just define m is the batch size, so that is be the length of output, whatever value passed to that, and y hat is calculated as dot product of input with the theta value, the weight and bias. Now j is calculated as 1 by m into sum of square of y hat minus y. So that is the cost function. Now let's define how we can calculate the gradient. Again, I need to pass x, y and theta, and then m is equal to length of y and then y hat is equal to x dot product with theta, and then the gradient is calculated as 1 by m. Now we're doing the x transpose and dot, right? So x transpose and then dot product with, because this is the differential terms. And then we will return the grad. So there we will return J. Now writing the stochastic gradient descent. So that function is actually where we randomly select the batch size, like the x value and y value, and then calculate the cost and gradient and update the theta value and store the cost function history on a very, like the with the number of iteration, whatever the size of it, that in that list. So defining stochastic gradient descent, again I need to pass x, y, theta, the initial value and learning rate, because we here now calculate the next theta value, right, with the help of gradient. And then number of iteration. First thing we need to do is defining m and then theta is equal to initialized and then defining this list, the cost function history list, with 0 as all value. Now I will start a loop and then I will choose a random training sample. In between the total data, so which number I will pick, so that will be my training sample for that particular iteration, and I will do it for the number of iteration we want. So now xi is equal to, again I am defining the array where x with the rand index and take all value of x and then reshape to get a array of list, to avoid a array of list. And then defining the y same as x, the same rand index I have chosen here as well. So this is my x and y value for that particular mini batch, and now I will calculate the gradient and I will pass the value of xi and yi and theta. So theta is initialized with the theta in it, and then I will calculate the theta, new theta. theta is equal to theta minus learning rate into gradient. Now I will calculate the loss. So this is my ith value of J history list, and that will be calculated from the cost function. And I have provided x, y, and theta. Now from this stochastic gradient descent function, I will return theta and J history. Now let's call this stochastic gradient descent from the main. So theta and J history will be calculated by stochastic gradient descent, where I will pass x, y. Actually, these are all defined. Number of iterations. Yeah. Now let's plot the cost over time. So I import the pie plot. And I'll plot the J history. And my X level is number of iterations, and my Y level is the cost. And then I'll just do plt dot. So, and after that I will print the last optimized value of weight, biased, and the cost. So print optimized weight. So that will be theta 1, and then optimized bias. So that will be theta 0, and then minimum cost function, cost value. So that will be J history, and then number of iterations minus 1, because it's an list index. So now let's try to mimic first what we have calculated in the paper, right? So to mimic that, so our random index is equal to 1 because we calculated for x is equal to 1, y is equal to 2. So that will be not 1, so that will be 0, and this will be again 0, and the number of iteration will be 1 only. So that will give me the same value of w and b as we have calculated in paper, that is 0.02 and 0.02. Let's run it. So this is 0.02 and 0.02, and you see the cost value is very high. It's not the minimum one. So now I will just update this and run it for 100 iteration and see what is my gradient descent. So see, this cost is saturated over a value, so that is almost lower than 1, and the weight and bias is calculated as 1 and 0.598, almost 0.6. So if I just increase this to 1000, I don't think it will differ much. So the cost value is now almost 0.5 and bias is 1.86 and weight is 0.07. You see, the cost versus iteration graph is almost saturated over the iteration. So it's very high. I think we have 16 as the initial value, and then it will saturate with the number of iteration. Thanks for watching this video. See you in the next video.